Studies on special behaviors of SCC using fiber and sand resources. R. Sooriya Priya. Postgraduate. Department of Civil Engineering. Sri Krishna College of Technology. Coimbatore, 641,042, India. Mrs. A. Vennila. Assistant Professor. Department of Civil Engineering. Sri Krishna College of Technology. Coimbatore, 641,042, India. Abstract: the thesis represents an investigation on mechanical behavior and microstructural analysis of self-compacting concrete. Concrete materials were weighed, batched and cast for M30 grade. A total of 8 cubes, 150 mm x 150 mm x 150 mm, and cylinder, 150 mm x 300 mm, were cast. All these cubes and cylinders were cast with partial replacement levels of calcite powder and quartz powder of varying proportions instead of using cement. Along with total replacement of foundry sand and 0.75% of basalt fiber were added. The use of large amount of quartz powder in combination with cementitious additions in concrete along with foundry sand has several practical and ecological advantages by reducing carbon dioxide emissions. The fresh properties of SCC were discussed using slump flow test, V-funnel test, L-box test, and U-box test were conducted. The specimens were cured and then tested for 7 days, 28 days. The microstructural properties were examined using SEM analysis, scanning electron microscopic. It was concluded that it holds good parameter on durability and fresh property test. It also increases the strength of hardened property. In this investigation it helps in reducing segregation resistance as it holds to be homogeneous and reduces the emission of carbondioxide. Introduction: in order to obtain high flowing characteristics, high amount of water reducers or superplasticizers were added. A type of aggregate mixture is added to gain the desired compactness. Alteration of fluid properties ensures a cohesive mix, which will keep the aggregate and paste together. Self-compacting concrete is used for repairs, restoration, and renewal construction. It is helpful in constructing highly stable and durable retaining walls. Self-compacting concrete is employed in the construction of raft and pile foundations. To determine the mechanical behavior of self-compacting concrete by using found dry sand. To determine better flowability, filling ability, and passing ability of self-compacting concrete. Self-compacting concrete or self-consolidating concrete was developed to improve the durability of concrete structures. It is a highly flowable type of concrete that spreads into the form without the need for mechanical vibration. In order to increase the volume of paste, cohesiveness of paste, stability of the concrete and to enhance deformability, the powder content is incorporated along with supplementary cementitious materials. Self-compacting concrete contributes a remarkable role on modern architectural and complex indeterminate structural construction. A development of self-compacting concrete. In 1983, there occurred a problem on durability of concrete structures. In order to overcome the problem, self-compacting concrete was created by Okamura in 1986, who is known as the father of SCC technology. Manufacturing of self-compacting concrete requires 3 main aspects to be fulfilled. B. Applications of self-compacting concrete. C. Objective of the project. D. Literature review. T. Parthiban, 2017, investigated on the durability of concrete by adding basalt fiber which do not contain any other additives. In this study, trial test for the concrete with cement, fine aggregate, coarse aggregate, and basalt fiber with 0%, 1%, 2% are conducted to prove the difference in durability parameters. Rapid chloride penetration test, water permeability test, sorptivity test were conducted for the concrete mix. In this experimental investigation it was concluded that fiber arrests the formation of micro cracks and thus in RCPT, WPT, ST the optimum value attained at 1% of fiber replacement. The test results found that 1% replacement holds good for durability parameter. Neelam Pathak and Rafat Siddiq, 2012, carried their study on effects of elevated temperatures on self-compacting concrete containing fly ash and spent foundry sand, which usually consists of ordinary Portland cement with 43 grade, class fly ash, fine and coarse aggregate and polycarboxylic ether-based superplasticizer. In this research the influence of class F fly ash with 3 percentages of 30%, 40%, 50% as cement replacement and replacing 10% of fine aggregate with spent foundry sand. For various percentages compressive strength test, split tensile strength test, RCPT, modulus of elasticity and fresh property tests, SEM analysis, and X, Ray diffraction tests have been evaluated and all these were heated up to 270 C, 1000 C, 2000 C, and 3000 C. From this study it was found that increase in strength attributes bending property of cement paste and thus the compressive strength increases between 2000 C and 3000 C. Augustine Uchechukuru Elanway, 2014, an evaluation on thesis of spent foundry sand as partial replacement of fine aggregate in concrete production. The material spent foundry sand was replaced in the proportions of 0%, 10%, 0.20%, 30%, and 40% by weight of fine aggregate and with a total of 5 mixes M0, M10, M20, M30 and M40 were prepared and cured for 3, 7, 28, 60, and 90 days. Tests were carried under compressive strength test, water absorption, and density and thus the results obtained that spent foundry sand can reduce the effects of absorption in concrete by 8% to 28% at 90 days of curing and also found that compressive strength reduces with increase in replacement levels and 10% replacement shows best behavior. Hafiz E. Ilyamani, 2014, et.al. evaluates the effect of filler types on physical, mechanical, and microstructure of self-compacting concrete and flowable concrete. It consists of cement with two groups of filler materials of 7.5%, 10%, 15%, and tests on hardened properties along with X-ray diffraction analysis, SEM analysis, thermogravimetric analysis were performed. It was evaluated that increase in filler type decrease segregation and bleeding and no negative effect occurs on non-pozzolanic filler materials. Arvind S.N., 2014, developed high-strength self-compacting concrete using mineral and chemical admixture. In this study consists of cement, fine aggregate, coarse aggregate, water, and the use of mineral admixture silica fume and viscous modifying agent with chemical admixture glenium B233 were used. An experimental investigation were carried out for fresh concrete and hardened concrete using FNARC guidelines. Results obtained that reduction of W/P ratio increases compressive strength and optimum dosage of chemical admixture maintains the self-compacting concrete. Calcite et.al. carried out an experimental investigation on the influence of basalt fiber and recycled concrete aggregate on self-compacting concrete through mechanical and durability tests. In this study the durability properties of self-compacting concrete elements were studied in carbonation depth. It has been observed high water absorption capacity, durability along with the behavior of RAC is lower than the normal concrete due to lack of bonding between recycled aggregate and cement mix. In order to overcome these deficiencies, can be eliminated by reinforcing it with discrete fibers. Special type of limitations is followed in fiber self-compacting concrete. Basalt fiber was varied as 0, 2, and 4 kg per cubic meter by replacing recycled concrete aggregate with various levels at 0%, 50% and 100% and compressive strength test, split tensile strength test, flexural strength test was carried out. Simultaneously further modifications were done using natural aggregate along with recycled concrete aggregate and tests on fresh concrete, hardened concrete was done. It was concluded that basalt fiber along with recycled concrete aggregate decreases in case of compressive strength. Similarly increase of basalt fiber increases the split tensile strength, flexural strength, and in carbonation depth. Gurpreet Singh and Ankush Thakur, 2018, Incorporation of waste foundry sand in concrete. Waste foundry sand is utilized as partial replacement of cement or partial replacement of natural aggregate or fully substituted as natural aggregate and as a supplementary addition for different properties of cement concrete. In this study compressive strength test, split tensile strength test, flexural strength test and modulus of elasticity of cement concrete of M30 grade and also the homogeneity of concrete ultrasonic pulse velocity method and water permeability is considered. Foundry sand is replaced as fine aggregate with 5 different replacement ratios 0%, 10%, 20%, 30%, and 40%. Thus, it was concluded that waste foundry sand with 30% replacement of fine aggregate gives maximum results and it reveals that water absorption values decreases with increase in replacement levels. Thus the increase in waste foundry sand increases in ultrasonic pulse velocity. Ilan Ozadabas, 2018, carried their study on investigation of the effect of basalt fiber on self-compacting concrete. Self-compacting concrete compared to the amount of binder in which it is insisted of blast furnace slag 10% and 30%, plasticizer additive 2.7%, basalt fiber with 1.6% in samples A and 3.2% in samples B. Slump flow test, V-funnel test, L-box test, compressive strength test, ultrasonic pulse velocity, water absorption, and weight per unit of volume tests were performed. It was observed from the experiments that the basalt fiber decreased the workability of fresh concrete and increased the compressive strength values. Sakthi Ganeshji, 2017, conducted study on mechanical and durability properties of self-compacting concrete in order to reduce the amount of cement content in concrete mix. Along with fly ash and superplasticizer and viscosity modifying agent, VMA, have been added to enrich the quality of workability. Fly ash with 15%, 20%, and 25% of cement replacement and tests on fresh concrete, filling ability, passing ability, and segregation resistance, and tests on hardened concrete have been evaluated. It was further concluded that 15% replacement of fly ash shows greater strength and suffers from chloride penetration. D.Indu and R. Elagovan, 2016, conduct an experimental investigation on optimum mix proportioning of high-strength self-compacting concrete for different grades, 30 MPa 80 MPa. In this study fly ash were added along with chemical admixtures. Numerous trials with increase in fly ash and decrease in water-cement ratio were done. Fresh concrete tests were observed and after casting, the compressive strength test, split tensile strength test and flexural strength test were obtained at 1, 7, 14, 28, 56, and 90th days respectively. It comes into conclusion that the flow ability, passing ability, and segregation resistance is within the limits. Systat which used for the empirical relationship investigates the selected range of combination of ingredients for the desired characteristics and the mathematical model predicts the proportions of concrete constituents strength and workability. M.Nitya, 2017, investigated on properties of concrete containing waste foundry sand for partial replacement of fine aggregate in concrete in which it is insisted of ordinary Portland cement, coarse and fine aggregate. 8 mixtures of fine aggregate were replaced using foundry sand in range of 5%, 10%, 15%, 20%, 25%, 30%, 35%, and 40%. Tests such as acid resistance test, alkalinity test, compressive test, split tensile test and flexural test have been done on 28th day. It was concluded that mechanical properties of concrete with waste foundry sand increases for 35% replacement and decreases for 40% replacement of fine aggregate. R. Vajumitha and Dr. P. Srinivasa Rao, 2013, an experimental investigation on strength and durability study of high-strength self-compacting concrete with different materials like quartz sand, quartz powder, viscous modifying agent for rheodynamic concrete, modified polycarboxylated ether-based superplasticizer and microsilica were used. However, it is more emphasized to the need of test on RCPT, slump flow, L-box V-funnel tests, and tests on hardened concrete. It made into remarkable result which indicates that chloride penetration of HSSCC shows less permeability of chlorides and reduces the cracks. Gawande Y.B., Professor P.B. Audit, 2017, demonstrates self-compacting concrete with partial replacement of sand by waste foundry sand. In this investigation waste foundry sand was carried out in the range of 0%, 10%, 20%, 30%, 40% by weight of M35 grade which was tested with compressive strength test, split tensile strength test, flexural strength test of self-compacting concrete and were compared with ordinary self-compacting concrete. It was observed that 20% of waste foundry sand shows maximum decrease in workability. Hence it was concluded that increase of waste foundry sand decreases the density of self-compacting concrete. Sarubdet al., 2018, have manufactured self-compacting concrete using calcite and fly ash. This paper consists of cement, coarse aggregate, fine aggregate, fly ash, and calcite where the calcite is an inorganic end filler material which improves the hydration rate of cement compound. Compressive strength test, flexural strength test and workability were conducted with 0%, 5%, 10%, 15% of calcite proportions. The results obtained that it overcomes the acid attack by using calcite and fly ash and increase in powder content increases workability of self-compacting concrete. K.Sathaskumarit al., 2017, experimented a study on the strength and analysis of basalt fiber in concrete. In this present experimental study, it aims to investigate the compressive, flexural, split tensile strength and the effects of different proportions of basalt fiber of length 12 mm in the mix. Test for the concrete is conducted with basalt fiber and without basalt fiber to show different proportions for M25 grade. The mix design for the fiber reinforced concrete is same as that of conventional concrete in case of small fiber volume of less than 0.5%. The addition of 0.5% of basalt fiber increases the compressive strength, and furthermore addition of 1% of basalt fiber gives maximum compressive strength, but basalt fiber with addition of 1.5% decreases the compressive strength. In the case of split tensile, flexural, the basalt fiber with 0.5% and 1% increases the strength, and furthermore addition of basalt fiber leads to decrement of strength. Pendhari Ankush R. 2017, represents the current utilization of fine sand in construction and mostly focuses on the amount of foundry sand used as a cementitious material. In order to overcome the disposal problem of industrial waste and to reduce the construction cost, the waste foundry sand have been used. This paper gives the remarkable results which indicates that the foundry sand is economical, and found that 30% replacement of waste foundry sand gives maximum compressive strength and flexural strength at 28 days. It was concluded that waste foundry sand is a good replacement of fine aggregate and helps in preparing green concrete. 2 materials used. A cement. It is useful in precast concrete. It is mainly used in fast track concrete. In situ concrete requiring fast striping time. It is used in self-compacting concrete. The cement and water form a paste that binds the other materials together as the concrete hardens. The ordinary cement contains 2 basic ingredients, namely argillaceous and calcareous. Ordinary Portland cement with 53 grade was used for casting all the specimens. Selection of the type of cement will depend on the overall requirements for the concrete, such as strength, durability, and etc. Properties of cement. B. Quartz powder. Quartz is a hard, crystalline chemical compound consisting of 1 part silicon and 2 part oxygen atoms, which are linked in a continuous framework of SiO2 silicon-oxygen tetrahedral. Quartz is commonly known as silica sand for producing float glass, fiberglass, automotive glass, and other types. Quartz has its important applications in the electronic industry. The specific gravity of quartz powder is 2.61. Chemical composition of quartz powder. See calcite powder. Calcite is a carbonate mineral and the most stable polymorph of calcium carbonate, CaCO3. Calcium carbonate powder is the filler material, improves the hydration rate of cement compound and consequently increases the strength at early ages. A beneficial influence on calcite powder on sulfate resistance. Calcite controls bleeding of concrete with low cement content and low susceptibility. D. Basalt fiber. Basalt fiber is made from a single material, crushed basalt, from extremely fine fibers of basalt and having better physico-mechanical properties than fiberglass. Its characteristics vary from the source of lava, cooling rate, and historical exposure to the elements. Basalt fiber is used in fiber reinforced polymer and in structural composites, which has high potential and getting lot of attention due to its high temperature and abrasion resistance. Basalt of high acidity, over 46% silica content, and low iron content is considered desirable for fiber production. Chemical composition of basalt fiber. E. Superplasticizer. SCC Viscocrete 20. He is a third-generation high-performance superplasticizer which is especially suitable for the production of concrete and mortar mixes. It gives high early strength development, powerful water reduction and excellent flowability. Applications of SCC Viscocrete. F. Coarse aggregate. In order to obtain a good concrete quality, aggregates should be hard and strong, free of undesirable impurities and chemically stable. Coarse aggregate conforming to N12620 are appropriate for the production of SCC. The amount of coarse aggregate used in self-compacting concrete is much lower when compared to the normal vibrated concrete. In the present study, coarse aggregate of 10 mm size is used for self-compacting concrete as per standard specifications. In order to avoid the aggregate blocking and to ensure the flowability, passing ability of SCC mix. Properties of coarse aggregate. Table V. Properties of coarse aggregate. Properties. Test results. G. Foundry sand. Foundry sand is a byproduct from the production of both ferrous and non-ferrous metal castings. It is high-quality silica sand with uniform physical characteristics. By foundry sand casting process, the metals are cast into particular shapes by melting into a liquid and then pouring it to the mold. Then the mold material is been removed after the metal has solidified as it cools. It is basically a fine aggregate that can be used in many ways as natural sands and manufactured sands. In the present study, fine aggregate is totally replaced by using foundry sand in order to increase its mechanical strength parameters and to hold good flowability, passing ability, filling ability, and segregation resistance. Properties of foundry sand. Table 6. Properties of foundry sand. 3 Mix proportions. Replacement ratio of calcite powder and quartz powder. In this study, cubes of 150 mm x 150 mm x 150 mm, and cylinder of 150 mm x 300 mm, were cast with 100% replacement of foundry sand, 0.75% of basalt fiber. Table 7 Mix proportions for self-compacting concrete. 4 Results and discussion. A. Fresh properties. SCC containing 100% of foundry sand was tested for slump flow, V-funnel, L-box, U-box. The results of fresh properties of self-compacting concretes with foundry sand are included in table below. The V-funnel flow times were in the range of 6-10 seconds. Test results of this investigation indicated that all SCC mixes meet the requirements of allowable flow time. In the above results, the L-box ratio H2/H1 for the mixes was above 0.8, which is as per FNARC standards. U-box difference in height of concrete in 2 compartments was in properties of self-compacting concrete. In terms of slump flow, all SCCs exhibited satisfactory slump flows within the prescribed range, which is an indication of a good deformability. All the fresh properties of concrete values were in good agreement for the flowability and passing ability to that of the values given by European guidelines. B. Hardened properties. A. Compressive strength test. Compressive strength of M30 grade concrete mixes with 100% replacement of fine aggregate using foundry sand and 0.75% of basalt fiber. Mix 1, 2.5% C.P plus 15% QP, Mix 2, 2.5% C.P plus 20% QP, Mix 3, 5% C.P plus 10% QP, Mix 4, 10% C.P plus 10% QP, at 7th and 28th days. Strength is given below. Table 9 Compressive strength results. Percentage replacement of calcite powder. Percentage replacement of quartz powder. Compressive. When the cement is replaced with 2.5% calcite powder along 15% quartz powder, there is an increase in compressive strength. Further replacement with cement as 2.5% calcite powder along with the addition of 20% quartz powder gives maximum compressive strength. When the cement is replaced with 5% calcite powder and 10% quartz powder, there is decrease in compressive strength. When the cement is again replaced with addition of 10% calcite powder and 10% quartz powder, results in decrement of compressive strength. B. Split tensile strength test. Split tensile strength of M30 grade concrete mixes with 100% replacement of fine aggregate using foundry sand and 0.75% of basalt fiber. Mix 1, 2.5% C.P plus 15% QP, Mix 2, 2.5% C.P plus 20% QP, Mix 3, 5% C.P plus 10% QP, Mix 4, 10% C.P plus 10% QP, at 7th and 28th days. Strength is given below. Table X Split tensile strength. Percentage replacement of calcite powder. Percentage replacement of quartz powder. Split tensile strength. When the cement is replaced with 2.5% calcite powder along 15% quartz powder, there is an increase in split tensile strength. Further replacement of 2.5% calcite powder along with the addition of 20% quartz powder gives maximum split tensile strength. When the cement is replaced with 5% calcite powder and 10% quartz powder, there is decrease in split tensile strength. When the cement is again replaced with addition of 10% calcite powder and 10% quartz powder, results in decrement of split tensile strength. See microstructural properties. A. SEM analysis. SEM, scanning electron microscopic, observations were examined on the self-compacting concrete mixtures with 100% of foundry sand and 0.75% of basalt fiber. Self-compacting concrete mixtures in SEM images which contains a cementitious material of 2.5% calcite powder and 20% quartz powder. V. Conclusion. On the basis of the results and discussions of this investigation, following conclusions can be inferred. For M30 grade concrete mix, the compressive strength and split tensile strength increases with 100% of foundry sand and 0.75% of basalt fiber. The compressive strength increases from 20.8 N/mm2 to 24.89 N/mm2 at 7th day, and from 30.2 N/mm2 to 34.2 N/mm2 at 28th day by replacing cement with 2.5% calcite powder and 20% quartz powder. The split tensile strength increases from 1.9 N/mm2 to 2.4 N/mm2 at 7th day and from 2.68 N/mm2 to 3.67 N/mm2 at 28th day by replacing cement with 2.5% calcite powder and 20% quartz powder. Further increase of calcite powder and decrease of quartz powder results in the decrement of compressive strength and split tensile strength. It was concluded that the strength increases at 2.5% of calcite powder and 20% of quartz powder with the incorporation of 100% foundry sand.